Right now, in the still air around you, trillions of oxygen molecules are drifting through your room, bumping gently into the wood of a bookshelf, the cotton of your sheets, the paper of a book left open on a nightstand. They are not doing anything to these objects. They collide, they bounce away, they collide again, over and over, in a kind of slow, patient conversation that has been going on since the walls of your room were built and the wood of your furniture stopped being part of a tree. Nothing is happening, and yet everything required for something enormous to happen is already present, hovering in the dark, waiting. This is one of the strange, quiet truths about the world you live in. You are, right now, surrounded by fuel, and surrounded by the thing that fuel burns in, and the only reason your room is not currently on fire is that the molecules bumping into each other do not, most of the time, have enough energy to actually react. They touch and separate, touch and separate. It is a bit like two people speaking different languages, passing each other in a hallway 1,000 times a day, capable of a conversation, but never quite finding the spark, so to speak, that lets the exchange begin. Your own body is doing something related, though slower and gentler. Inside nearly every cell you have, oxygen you breathed in a few moments ago is combining with sugar that came from something you ate, and that combination is releasing energy that keeps you warm, keeps your heart drawing itself closed and open, keeps you, at this very second, alive enough to be lying here listening. This process is controlled, wrapped in careful biological machinery, spread out gently over many small steps so that it never gets hot enough to hurt you. But it is, underneath all that careful control, the same basic kind of chemistry as the one that would happen if that same sugar were dropped into a much faster, much hotter, much less controlled version of the same reaction. Your body is performing an extremely slow, extremely careful burn, one that took nature billions of years to tame into something survivable. So here is the first strange thing worth sitting with tonight, turning over slowly, like a stone in your palm, the difference between the calm molecular bumping in your room and the violent glowing event we call fire is not a difference in ingredients. It is a difference in speed, and in what starts things off, and in how the released energy behaves once it exists. Somewhere between the gentle bumping of oxygen against wood and a full blaze, something crosses a threshold, and once it crosses, it doesn't stop on its own. Now, let's think about fire itself for a moment, the thing you have seen 1,000 times without really looking at closely. Picture a candle. Maybe you have one somewhere in your home, sitting in a drawer or on a shelf, unlit right now. When it is lit, you see something that looks, very convincingly, like an object. It has a shape, it has edges, it flickers, but it seems to have a body, a form that holds together, something you could point to and say, "There, that is the flame." But here is the puzzle, the one that people rarely stop to think about, because flames are so common, we stop being curious about them. A flame is not a thing in the way a stone is a thing, or a spoon is a thing, or even the way a cloud is a thing. A stone is made of the same atoms, sitting in roughly the same arrangement, whether you look at it now or an hour from now. But a flame is never made of the same atoms from one instant to the next. It is not an object holding still in space. It is an event, continuously happening, continuously rebuilding itself out of new material, moment by moment, so quickly
that your eye cannot tell the difference between the thing existing and the thing constantly being remade. Think of it this way. Imagine a river, the kind you might have stood beside once, watching the water rush over a particular rock and curl into a particular pattern of ripples just downstream of it. If you come back the next day, the ripple pattern might look exactly the same. You could photograph it, and it would look like an object, a fixed shape sitting in the river. But not one drop of water in that ripple is the same water you saw the day before. The shape persists. The water does not. The shape is not a thing, it is a pattern, held in place by a continuous flow of something moving through it and being replaced. A candle flame works something like this. The flame you see is not a static blob of burning material sitting still above the wick. It is the visible signature of a process. Melted wax being drawn up the wick by the same kind of capillary action that pulls water up into a paper towel. The heat of the flame turning that liquid wax into a vapor. That vapor mixing with oxygen from the air around it, and that mixture reacting so quickly that it glows with heat and light. All of that is happening continuously, in a kind of tight, self-sustaining loop, dozens of times each second. The flame you see holding its teardrop shape is really a shape being rebuilt, instant after instant, out of freshly vaporized wax and freshly arrived oxygen, exactly the way the ripple in the river is rebuilt out of freshly arrived water. This is worth sitting with for a while tonight, because it reorganizes something in how you might picture fire. When you were small, maybe someone told you fire was a thing you could touch, an object with a boundary, something that could burn you if you got too close, and all of that was true in a practical sense. But if you had asked, at 4 or 5 years old, what a flame was actually made of, the honest answer would have been strange and a little unsettling. It is made of whatever fuel happens to be vaporizing at that exact moment, glowing while it reacts, and then it is gone, replaced by the next batch, and the next, in a chain that might run for hours if the candle is long enough and nobody blows on it. There's an old story, possibly more legend than fact, but worth mentioning gently, about ancient thinkers who wrestled with this very confusion. Some early Greek philosophers, centuries before anyone understood atoms or oxygen, proposed that fire was one of the fundamental building blocks of the universe, a substance in its own right, alongside earth, water, and air. It's an understandable guess. If you only trust your eyes, fire really does look like a kind of stuff, a fourth ingredient poured into the world, alongside solid, liquid, and gas. It took a very long time, many centuries of careful watching and careful arguing, for people to realize that fire isn't a substance you can point to and put in a box. It's a happening. It's what a reaction looks like while it's in progress. The way a wave is not water itself, but a shape moving through water. That confusion, in a way, is the confusion this whole story tonight is built around, and it's a comfortable one to fall asleep thinking about, because there's no urgency to resolving it, no danger in wondering slowly. A flame looks solid because your eyes are slow and the reaction is fast. It looks like an object because it holds a stable shape, even while every particle inside that shape is being replaced almost as fast as you can notice it. And underneath that shape, at a scale too small to see, even if you leaned in close with your face just inches from the wick, are the same two ingredients that were quietly bumping into each other in the dark of your room a few minutes ago. fuel, and oxygen. Only now, they've crossed some threshold and started reacting for real. What that threshold actually is, what makes molecules go from politely bouncing off each other to violently rearranging themselves into something new, is where we'll drift next. Slowly, the way heat drifts through a cooling room, settling gently until you're not quite sure when you stopped listening and started dreaming.
Long before anyone wondered what fire was made of, in the philosophical sense, someone was simply trying to keep one alive through a cold night. That's worth sitting with for a moment. The question of what fire is came very late in human history. The question of how to keep it burning came very early, so early that we can't actually find its beginning. We can only find traces, and traces are strange things to build a story from, because a trace never quite tells you the whole truth. It just tells you that something happened, once, in a place, and left a mark. Consider a cave in southern Africa called Wonderwork, a name that means, fittingly, wonder work. Deep inside it, in layers of sediment that have been resting undisturbed for roughly 1,000,000 years, researchers found tiny fragments of burned bone and ash, sitting far enough from the entrance that ordinary lightning-struck brush fires seem an unlikely explanation. A fire that far inside a cave usually means someone carried it there, not lit it there, necessarily, not from scratch, but carried it, tended it, fed it. That's already a remarkable thing to imagine, long before you get anywhere near a spark. Somebody, or some collection of somebodies, understood that the glowing thing at the mouth of the cave could be moved without dying, could be walked deeper into the dark, deliberately, on purpose, and kept alive once it got there. But here's where the historian's caution has to come in gently, the same caution a careful scientist brings to any old and faint evidence. Finding ash is not the same as finding proof of daily, dependable fire use. It could be a single event. It could be one extraordinary night in 1,000,000 uneventful ones, the kind of night that happens by chance and is never repeated. Archaeologists have learned to be wary of turning one hearth-shaped smudge into an entire chapter of the human story. What they look for instead, patiently, layer by layer, is repetition. Not just one fire, but many fires, in the same place, over and over, century after century, the kind of pattern that only makes sense if fire had become a habit, a tool, a fixture of ordinary life, rather than a stroke of luck. That kind of repeated, dependable evidence starts showing up more clearly somewhat later, around 300,000 or 400,000 years ago, at places with names like Chesim Cave, in what's now Israel, or Gesher Benot Yaakov, near the edge of an ancient lake. There, researchers have found not just scattered ash, but clustered patches of burned flint and charred wood, gathered in the same few spots, again and again, the way a fire pit in a backyard gets used summer after summer, long after the grass around it has gone permanently bare. That clustering is a kind of signature. Wildfires wander. Wildfires don't return to the same 6 feet of ground for generations. People do. And once fire became something people could depend on, even loosely, even before anyone fully understood how to strike it from nothing, everything around it started to change. Cooking is the change most often talked about, and for good reason, though it's worth saying clearly that plenty of the details here are still argued over by careful researchers, not settled fact carved in stone.
There's a compelling idea, associated especially with the researcher Richard Wrangham, that cooked food may have quietly reshaped the human body over hundreds of thousands of years. Cooking breaks down fibers and proteins before they ever reach your teeth. It does a portion of the digesting work outside the body, in the pot or on the coals, instead of inside a long coil of gut. If that idea holds up under the ongoing scrutiny it deserves, it would mean a smaller stomach and a shorter digestive tract could still keep a person adequately fed, freeing up energy that a body could spend elsewhere. Some researchers have wondered whether that freed energy helped support a brain that was, across the same stretch of time, quietly growing larger and hungrier for fuel. It's a graceful idea. It is also, importantly, still a hypothesis, argued over politely, and sometimes not so politely in journals and conference halls. And it's the kind of claim worth holding loosely, rather than repeating as settled history. What we can say with more confidence is simpler and almost more remarkable for being so plain. Cooked food is easier to chew, easier to digest, and often safer to eat, since heat kills many of the small organisms that make raw food risky. That much needs no elaborate theory. Anyone who has ever gotten sick from undercooked meat already understands it in the most personal way possible. Warmth is the other obvious gift. So obvious, it barely needs explaining, though it's worth pausing on anyway, since it shaped where and how people could live. A campfire doesn't just keep hands from going numb. It opens up entire seasons and entire latitudes that would otherwise be unlivable. Without a reliable fire, a cold night in a northern climate is a serious danger, not a discomfort, and a long winter is close to a death sentence for a body without fur thick enough to hold its own heat. Fire let people push into colder places, sleep through colder nights, and survive stretches of the year that would otherwise have kept them pinned to warmer ground. And then there's protection, which is easy to forget about now, sitting somewhere safe, with the doors locked, but would not have been easy to forget about then. Large predators, generally, do not like fire. The flicker, the crackle, the smell of smoke, the sudden bright, unpredictable movement of flame in the dark. These things unsettle animals, whose eyes and instincts are built for a world of steady moonlight and quiet shadow. A ring of firelight around a sleeping group was not decoration. It was a wall, invisible and warm, that many large animals simply chose not to cross. People sleeping near a fire were sleeping inside a boundary that predators respected far more reliably than any fence of branches could have offered. Fire also changed the shape of the evening itself, and this part is more speculative, gently so, resting on reasoning rather than direct evidence, but it's a lovely thing to consider anyway. Before controlled fire, once the sun went down, there wasn't much to do except sleep, since the dark made most tasks impossible, and most activity dangerous. A fire pushed a little pocket of daylight into the night, small and orange instead of vast and blue, and inside that pocket, people could keep working a little longer, keep talking a little longer, keep sitting together, instead of scattering off alone into separate patches of darkness. Some researchers who study the origins of human storytelling and social bonding have wondered whether the campfire, as a shared circle of light and warmth, played a real part in the shape those evenings took, encouraging longer conversation, looser conversation, the kind of talk that isn't about the urgent business of the day but about something else entirely. Memory, myth, whatever passed between people once the practical talk had run its course. It's a tender idea, hard to prove and easy to romanticize, so it's worth holding the way you'd hold any old photograph, with a story attached that nobody left behind to confirm. What is more solidly documented, because it leaves harder evidence behind, is fire's role as a craftsman's tool, rather than merely a source of comfort. Heat-treating stone, for instance, applying careful warmth to certain kinds of rock before knapping it into blades, made the stone easier to shape with a controlled, glassy fracture, instead of a stubborn, crumbling one. Fire hardened the tips of wooden spears, drove moisture out of green wood, and thinned it toward a point. Fire cleared land, in some places and eras, opening ground for new growth or driving game toward waiting hunters. None of this required understanding fire in any deep sense. It required only patient observation, trial, and memory passed from one pair of hands to another, the ordinary craft of watching what works and doing it again. And from craft it is only a short, natural step toward something less practical, and harder to pin down. The fires people built, not to cook, or to stay warm, but simply to gather around, to mark an occasion, to look at.
Something worth noticing about a fire built for its own sake, one nobody strictly needed for cooking or hardening a spear tip, is that people still had to understand it well enough to keep it going, or at least well enough to imitate whoever in the group did understand it. That practical understanding, built from centuries of trial and repetition, was really a working knowledge of chemistry, arrived at without anyone using that word or needing it. It's worth slowing down now and looking at what was actually happening inside all those fires, ceremonial and practical alike, at the level too small to see by firelight. Fire is a form of oxidation, and oxidation is a much larger, quieter category of event than the word usually suggests. A nail left out in the rain oxidizes, so does a sliced apple browning on a plate, and so does the slow, patient work that turns green copper roofing that pale, chalky blue-green over decades. All of these are, in a chemical sense, cousins of the fire crackling in a hearth. What separates a rusting nail from a burning log isn't really a difference in kind. It's a difference in speed, and in how visible the process chooses to make itself. Rust is oxidation moving so slowly that you'd need a calendar, not a clock, to watch it happen. Fire is the same basic event, but compressed into seconds, loud about it, throwing off light. To understand why some oxidation crawls and some oxidation roars, it helps to think about what a molecule actually is: a small, particular arrangement of atoms held together by bonds that are, in a real sense, a kind of stored potential. Picture a compressed spring, or better, a boulder resting partway up a hill, held in place by nothing more than friction and its own contours. There's no substance sitting inside that boulder that you could scoop out and call energy, but it has potential, by virtue of where it sits and how it's arranged, to move, to change position, to end up somewhere lower and more settled if given the right nudge. The molecules in a piece of wood, or a candle's wax, or the gasoline in a lawnmower's tank are arranged the way that boulder is arranged, not at their lowest, most settled configuration, but held up in a higher one, atoms bonded together in patterns that took energy to assemble, and that would, given the chance, rearrange into something more stable. Oxygen is the partner that offers them that chance. When fuel molecules and oxygen molecules collide with enough force, and in the right way, old bonds break and new ones form. Carbon atoms that were locked into long chains alongside hydrogen and other carbons end up instead paired with oxygen, forming carbon dioxide.
Hydrogen atoms end up bonded to oxygen as well, forming water, which is why a candle flame, oddly enough, is quietly producing something you'd normally associate with rain. These new arrangements, carbon dioxide and water vapor, are more stable than the arrangements they came from. They sit lower on that hillside, and the difference between where the atoms started and where they end up doesn't vanish. It doesn't get stored anywhere as a kind of leftover residue. It shows up as motion. The newly formed molecules go flying outward, vibrating and colliding with tremendous energy, and that agitated, restless motion of countless molecules, bumping into each other and into the surrounding air, is what heat actually is. Not a substance poured out of the fire, like water from a jug, but a description of how fast and how forcefully the molecules nearby have started to move. A reaction that releases this kind of energy outward, rather than needing energy fed into it continuously, is called exothermic, and combustion is one of the more dramatic, everyday examples of it. But here's the puzzle, that a woodpile, sitting quietly in a shed, answers on its own, without any chemistry lesson required. If burning wood releases so much energy, why doesn't wood simply burn on contact with the air surrounding it every single day, sitting there, in a shed full of oxygen? The boulder on the hillside offers the answer again. Even a boulder perched high up, with a long, energetic roll ahead of it if it starts moving, can still be sitting in a small dip or hollow near the top, a little lip of ground it has to be pushed up and over before gravity takes hold of it properly. Until something provides that initial push, the boulder can sit there indefinitely, full of potential and going nowhere. That small uphill push, in chemistry, is called activation energy, and it's the reason a match is needed at all. Striking a match, holding a flame to kindling, focusing sunlight through a lens onto dry leaves. All of these are ways of supplying that initial nudge, jostling a small number of fuel and oxygen molecules hard enough that they finally react, releasing their stored energy, and, crucially, releasing enough of it to shove their neighbors over the same small lip. That's the moment a fire stops being an isolated event and becomes something that sustains itself, and it depends on a strange, short-lived kind of particle called a radical. When a molecule gets jostled hard enough, whether by heat or flame or a spark, it doesn't always break apart neatly into finished products right away. Sometimes it splits first into a fragment that's missing something it needs, an atom or a molecule with an unpaired electron, hanging there incomplete and, as a result, extremely reactive. Think of someone at a crowded, jostling gathering who's suddenly separated from the hand they'd been holding on to, and who doesn't stand there patiently waiting to find that exact hand again. They reach out for whatever hand is nearest, immediately, almost without choosing. A radical behaves something like that. It doesn't wait around for the ideal partner.
It grabs the nearest molecule it can react with, tearing that molecule apart in turn, producing more radicals, more unstable fragments, each reaching out for their own nearest neighbor. Each of those reactions releases a bit more of that outward, agitating energy too, which keeps the whole surrounding region hot enough to keep producing more radicals from more fuel. This cascading, self-feeding sequence is called a chain reaction, and it's the real engine underneath a sustained fire. Not just the burning of one molecule after another in isolation, but a spreading, branching relay of these hungry, unstable fragments, handing energy and reactivity along to their neighbors. People who study fire safety and fire behavior have a simple, old way of summarizing what a fire needs to exist at all, usually drawn as a triangle, with fuel on one side, oxygen on another, and heat, meaning enough energy to keep supplying that activation push, on the third. Take away any one side, and the triangle collapses,
the way a three-legged stool tips over the moment you saw through any single leg. Starve a fire of fuel, and it goes out for lack of anything left to react with. Smother it, cutting off its access to oxygen, and it goes out even with plenty of fuel remaining, unburned, right there. Cool it, drawing away that agitated molecular motion faster than the chain reaction can replace it, and it goes out even with fuel and oxygen both still present in abundance, which is part of why water works as well as it does, not by pushing the fire away but by absorbing that frantic motion into itself until there isn't enough left to keep pushing new molecules over the hill. Later on, chemists studying fire more closely realized the triangle, useful as it was, left something out, something separate from fuel, oxygen, and heat individually. You could have all three of those present, in generous supply, and still stop a fire cold by interrupting the chain reaction itself, breaking the relay of radicals passing their reactivity along from molecule to molecule, the way certain chemical fire-suppressing agents work, not by removing fuel or oxygen or cooling things down, but by intercepting those unstable, reaching fragments before they can grab their next neighbor. So the triangle grew a fourth side, becoming a tetrahedron in the diagrams, with the chain reaction sitting there as its own distinct requirement, as essential to a fire's survival as anything it burns or breathes. Understanding all of this still leaves an ordinary, visible mystery standing right in front of you every time you watch a candle or a hearth. Given only these ingredients, fuel, oxygen, a nudge of activation energy, and a chain reaction quietly relaying itself forward, why does the result take the particular shape it does, tapering upward, restless, always leaning and reaching the way it does, rather than sitting there as some shapeless, sourceless glow?
The answer, it turns out, has less to do with fire itself and more to do with something as simple as the fact that hot things rise. The gases produced right at the base of a flame, freshly heated, freshly reacting, are lighter, less dense, than the cooler air surrounding them, the same way a hot air balloon strains upward, simply because the air inside it has been persuaded to take up more room per molecule than the air outside. So that column of heated, reacting gas does what any buoyant thing does. It rises, and as it rises, it pulls cooler, oxygen-rich air in behind it, in underneath it, to replace what just left, which feeds the reaction fresh oxygen right where the flame needs it most, at its base, which keeps the whole restless cycle going, rising and drawing and rising again, which is why a candle flame in still air settles into that familiar teardrop, narrow at the bottom, widening, then tapering back to a point, and why the faintest draft sends it leaning, guttering, reaching sideways as though startled. There's no mystery of will in it, no flame reaching for anything in particular. It's convection, plain and steady, the same physics that stirs a pot of soup from below. But knowing why a flame takes its shape still doesn't tell you what, exactly, you're looking at when you look at one. And this is where it helps to slow down and ask a more basic question than it seems. What is glowing? Part of the answer is heat itself, glowing on its own terms, a phenomenon called incandescence, which simply means that anything hot enough will radiate light, whether or not it's burning, whether or not any chemistry is involved at all. Heat an iron rod in a forge and it will start to glow dull red, then orange, then, if you could get it hot enough without melting it, yellow and white, purely because its atoms are vibrating with such intensity that they shed some of that energy as light. A flame does something similar, though the glowing object in this case isn't a rod of iron but something far smaller and more fleeting, tiny particles of soot,
unburned carbon, briefly incandescent as they pass through the hottest part of the flame before either finishing their combustion or drifting off as smoke. This is why a candle flame or a campfire glows that familiar warm yellow-orange, and why the middle and upper regions of such a flame look almost solid, almost like a glowing fabric, when really what you're seeing is a dense suspension of these carbon specks, each one radiating according to its temperature, each one existing for only a fraction of a second before it's consumed or swept away and replaced by the next. That's one source of light, but there's a second one, working alongside it, that has nothing to do with heat as such, and this is the part that tends to surprise people. It's called chemiluminescence, and it means light produced directly by a chemical reaction as a byproduct of the reaction itself, independent of how hot anything is. When certain molecules form during combustion, they don't settle immediately into their calmest, lowest energy arrangement. They form first in an excited state, jittery, overcharged, holding a bit of extra energy left over from the reaction that just built them, and a moment later, sometimes within nanoseconds, they relax down into their stable form, releasing that extra energy as a photon of light, of a very particular color, or more precisely, a very particular wavelength, determined by exactly how much energy was released in that specific step of the reaction. This is why the base of a candle flame, right around the wick, glows with a thin blue that looks almost otherworldly against the warm yellow above it. That blue isn't soot glowing from heat. It's coming from excited molecular fragments, things like CH and C2, radicals formed briefly in the earliest instant of combustion, casting off light as they settle, before the reaction has produced enough soot for incandescence to take over and drown out that blue with a much brighter yellow-orange. And this is exactly where a very natural but mistaken instinct tends to creep in, the assumption that because that blue looks cooler and calmer to the eye, the way blue often reads as cool in 100 other contexts, ice, water, a winter sky, it must mean that part of the flame is less hot. In fact, it's usually the opposite. The blue region at a candle's base tends to be hotter than the yellow above it, not because blue light is inherently a signature of higher heat in every situation, but because in a flame specifically, the blue is coming from a different mechanism entirely, chemiluminescence from freshly reacting gases, happening in the zone where combustion is most complete and most vigorous. While the yellow above comes from incandescent soot particles that have had time to drift upward, cool slightly, and glow at a lower temperature even while still burning. So color and temperature are related, but they aren't the same conversation, and conflating them is one of the easiest mistakes to make when looking at a fire. A star's color really is a fairly reliable guide to its surface temperature, red stars cooler, blue stars hotter, because starlight comes almost entirely from thermal radiation, incandescence on an enormous scale, with nothing else muddying the signal.
A flame, by contrast, is mixing two different kinds of light making at once, and asking you to read temperature from color the way you'd read it from a star gives you the wrong answer more often than the right one. There's a third layer to all of this, which is where fire starts to reveal something almost like a fingerprint, and it depends on what, precisely, is burning. Every element, when given enough energy, will release light at very specific wavelengths, and only those wavelengths, because the electrons circling its atoms can only jump between certain fixed energy levels, never anywhere in between, the way a person climbing a ladder can stand only on the rungs and nowhere along the space between them. When an electron absorbs enough energy to leap up to a higher rung and then falls back down, it releases exactly the energy difference between those two rungs,
as a photon of one specific color, no other. Sodium does this in a way that produces a strong, unmistakable yellow-orange, the same color you may have noticed in old sodium streetlights. Copper tends toward blue-green. Strontium and lithium lean red. Potassium gives a pale violet, easy to miss unless you know to look for it. This is the whole basis of fireworks, colored flares, and the flame tests still taught in introductory chemistry classes, where a chemist dips a clean wire into a metal salt and holds it into a flame just to watch what color announces itself. It's also, historically, how several elements were discovered in the first place, not by isolating a new substance and then studying it, but by noticing a line of color in a flame's spectrum that didn't match anything known and going looking for whatever was producing it. Robert Bunsen, working in Heidelberg in the late 1850s alongside the physicist Gustav Kirchhoff, built a burner specifically designed to produce a nearly colorless, low-soot flame so that when he introduced a sample into it, the flame's own light wouldn't drown out the faint, telltale colors the sample itself produced. That collaboration, using little more than a modified gas burner and a prism, went on to reveal two new elements entirely, named for the very colors their spectra had shown: cesium for the sky-blue lines it cast, rubidium for a deep red no one had catalogued before. All of which is to say that the color of a flame isn't decoration. It's a kind of message, written in light, about exactly which atoms are present and exactly how much energy they're shedding as they settle back down. There's still more happening in that glow than color alone can capture, though, because not everything a fire gives off is something your eyes were ever built to see.
Let it settle there a moment, that idea of a fire announcing its contents in light, because it leads naturally to a quieter and stranger question. Why does a fire start when it does, and not a moment sooner or later? A birch log has been sitting in a woodpile all summer, entirely stable, entirely uninterested in becoming flame, and then one evening it catches, and burns, and within an hour is mostly gone. Nothing about the wood itself changed in that time. What changed was a set of conditions lining up, and it's worth walking through what those conditions actually are, slowly, because the word ignition gets used casually, as though it names a single event, when it actually names a small cluster of related but distinct thresholds. Start with flashpoint, because it's the easiest to picture. Imagine a shallow dish of gasoline sitting in a cool garage. The liquid itself doesn't burn. Liquids essentially never do. What burns is vapor, the molecules that have escaped the surface of the liquid and drifted into the air above it, mixed with oxygen in just the right proportion. Every volatile liquid is constantly losing a few molecules to the air this way, even at room temperature, the same restlessness that lets a puddle of water slowly vanish without ever boiling. The flash point of a liquid is the lowest temperature at which enough of those vapor molecules have escaped into the air above it that, if you brought a flame or a spark close enough, the vapor would catch, flare briefly, and then go out again because the liquid beneath wasn't yet hot enough to keep replenishing the vapor at the rate needed to sustain a flame. Gasoline's flash point sits well below room temperature, somewhere around -40 degrees Fahrenheit, which is part of why it's so unnervingly easy to ignite, even on a winter morning. Diesel fuel, by contrast, has a flash point over 100 degrees higher, which is a large part of why you can, carefully, drop a lit match into a puddle of diesel and watch it simply extinguish, something you would never want to try with gasoline. The flash point isn't a statement about how flammable a substance is, in some vague overall sense. It's a very specific number, telling you the temperature at which the air just above the liquid becomes, briefly, a flammable mixture. Auto-ignition temperature is a different threshold, and a more unsettling one, because it requires no spark, no match, no outside flame at all. It's the temperature at which a substance will ignite purely from its own heat, with no external ignition source needed. Paper has an auto-ignition temperature widely cited as around 450 degrees Fahrenheit, a number that entered popular culture through Ray Bradbury's novel, though Bradbury himself noted he'd gotten the figure from a fire department rather than testing it in his own oven, and the true value varies somewhat depending on the type of paper and how the test is run. Diesel fuel, sitting inside a diesel engine, never needs a spark plug at all. The engine simply compresses air tightly enough, and compressing a gas heats it, a principle you can feel yourself if you've ever pumped a bicycle tire and noticed the pump barrel growing warm under your palm. Compress that air enough, injecting fuel at just the right moment, and the heat of compression alone is sufficient to ignite it. That's the entire operating principle behind the engine Rudolf Diesel patented in Germany in 1892, a design he pursued partly out of a very practical frustration with how much energy the spark ignition engines of his day wasted as heat. But knowing a material's flash point or its auto-ignition temperature still doesn't fully explain why a spark, something lasting a tiny fraction of a second and containing almost no total energy at all, can set off a fire that goes on to consume an entire forest or an entire building. The heat contained in a single spark from a flint striking steel is genuinely tiny, barely enough to warm a pinprick of material by any meaningful amount. What a spark does isn't heat an object. What it does is start a reaction in one infinitesimally small spot, and then let that reaction feed itself. This is the idea of a self-sustaining chain, and it's worth sitting with, because it explains so much about why fire behaves the way it does. Combustion, once it begins in some small pocket of fuel and oxygen, releases heat. That heat radiates outward into the fuel immediately next to it, raising that neighboring fuel to its own ignition point, so it begins to burn too, releasing its own heat, which warms the fuel next to that, and so on, outward, in a wave. A spark doesn't need to supply the energy for the whole fire. It only needs to supply enough energy to get that very first, very small patch of material past its ignition threshold, after which the fire supplies all its own fuel for continuing, the way a single toppled domino doesn't need any further pushes to knock down the 1,000 dominoes lined up behind it. This is where kindling earns its old, practical wisdom, the kind that predates any formal chemistry by many thousands of years, but tracks the science exactly. Small twigs and dry grass catch more easily than a fat log for two reasons that work together. The first is surface area. A log, sitting in a fire, has most of its volume tucked away inside itself, insulated from the surrounding oxygen, with only its outer surface actually exposed to air. Split that same log into thin splinters and shavings, and you've taken the same amount of wood and spread far more of it out into direct contact with oxygen and with heat. It's the same reason a spoonful of granulated sugar dissolves in a cup of tea within seconds, while a single sugar cube of the same weight takes minutes, stirred or not. Break something into smaller pieces, and you multiply the surface available for a reaction to happen across. The second reason is thermal mass, meaning simply how much material there is to heat up before that material reaches its ignition point. A thin twig has very little mass to warm, so a small flame can push all of it past ignition temperature quickly. A thick log has enormous mass,
absorbing heat from a small flame and dispersing it through the interior of the wood almost as fast as it arrives, so that the surface never quite gets hot enough for long enough to catch. This is why anyone who has built a campfire, whether last month or 2,000 years ago along a riverbank, instinctively reaches for the thinnest, driest material first, coaxes that into a real flame, and only then feeds in progressively thicker wood, letting each stage generate enough sustained heat to ignite the next. And oxygen supply matters just as much as fuel and heat, forming the third leg of what's sometimes taught as the fire triangle: fuel, heat, and oxygen, all three needed together, none sufficient alone.
A pile of dry leaves stuffed tightly into a bag will resist catching fire far more stubbornly than the same leaves loosely scattered, because the packed leaves starve each other of the air a flame needs to keep drawing on. It's why a fire that seems to be dying down will often flare back to life the instant someone opens a damper, or a window, or simply fans it, feeding in a fresh supply of oxygen the flame had begun to exhaust from its immediate surroundings. Catalysts complicate this picture a little further still, substances that don't get consumed in a reaction themselves, but that lower the amount of energy needed to get the reaction started, letting ignition happen at temperatures where it otherwise wouldn't. Certain metal oxides, present as tiny impurities in some materials, can act this way, quietly making one batch of what looks like the same substance measurably easier to ignite than another batch that seems, to every ordinary test, identical. Heat itself, once it exists, has to travel somehow, and it does this in three distinct ways, each with its own quiet logic, and understanding them helps explain almost everything about how a flame behaves once it gets going. The first is conduction, which is heat moving through direct contact, molecule bumping into molecule, passing along its jostling energy the way a line of people might pass a bucket hand to hand without anyone actually walking anywhere. Touch one end of a metal poker to the coals of a fire, and, given enough time, the far end grows warm too, even though no flame ever touches it, because the agitated atoms at the hot end collide with their neighbors, and those collide with theirs, a chain of tiny handoffs traveling down the metal. Wood conducts heat far more slowly than metal, which is part of why a wooden spoon left resting in a hot pot stays cool enough to grasp, while a metal one would not, and it's also part of why a log's interior, as mentioned before, can stay cool even while its surface chars, the heat arriving from outside faster than the wood's own sluggish conduction can carry it inward. The second mechanism is convection, and this one only works in fluids, meaning liquids and gases, substances whose particles are free to actually move from place to place, rather than simply vibrating in a fixed position. When air near a flame is heated, it expands, the way any gas does when warmed, and expanding makes it less dense than the cooler air around it, and less dense material floats upward through denser material for the same reason a cork floats up through water. So the heated air rises, carrying its warmth away from the flame and upward into the room or the sky, and as it rises, cooler air flows in along the ground to replace it, air that then gets warmed in its turn, rises in its turn, and the whole cycle repeats itself as a continuous, self-sustaining current. This is convection, and it's the same principle at work whether you're watching steam curl up from a cup of tea or feeling a draft along the floor near a fireplace, even as the air above your head feels stifling and warm, because the fireplace
is constantly drawing in cool air low and expelling hot air high, an invisible wheel turning in the room. The third mechanism, radiation, doesn't need any contact or any moving fluid at all. It's heat, traveling as electromagnetic waves, the same basic family of waves as visible light, just at wavelengths our eyes mostly can't detect, and it can cross empty space, which is precisely how the sun, 93 million miles away, with nothing but vacuum in between, manages to warm a person's skin. Stand near a campfire on a still night, close enough to feel its heat on your face, and most of what you're feeling on the side facing the flames is radiation, arriving in straight lines the way light does, which is why you can feel the fire's warmth on your front, while your back, shielded from that direct line of sight, stays cold, something no amount of convected warm air alone would fully explain, since warm air would tend to rise up and around, rather than radiate outward in a beam. All three of these mechanisms, conduction, convection, and radiation, are almost always happening at once around any fire, layered on top of each other, though their relative importance shifts, depending on the situation, the materials involved, and how close you happen to be standing.
It's convection, in particular, that answers one of the most familiar and yet oddly overlooked questions about fire, which is simply why flames point upward. A candle flame, a campfire, a struck match, held in almost any orientation, will still send its visible fire reaching toward the ceiling rather than the floor, and this isn't some intrinsic property of fire itself, some inner compass fire carries around, but a direct consequence of gravity acting on the hot gases the flame produces. As the flame heats the surrounding air and the gases released by the burning fuel, that heated material becomes buoyant, exactly as described a moment ago, and buoyant material rises. The rising column drags fresh air in from below to replace what's departed, and that fresh air feeds the reaction with new oxygen, which sustains more burning, which produces more heat, which rises further still, an ongoing loop of cause and effect that shapes the flame from underneath even as it appears to simply glow there in place. The classic teardrop silhouette, narrow near the wick or the fuel source and widening as it climbs, comes from this same rising current. Near the base, the flame is anchored close to the fuel, hot and turbulent but compact. As the hot gases ascend, they cool slightly, slow down, and spread outward the way smoke does higher up a chimney, giving the flame its familiar tapered, flickering shape, a shape that dances and shifts constantly because the rising convective current is never perfectly smooth, always wobbling, always drawing in air unevenly from the sides. Remove gravity from this picture, and something genuinely strange happens, something that wasn't well understood until astronauts and researchers began deliberately lighting small, carefully controlled flames aboard orbiting spacecraft. Without gravity, there's no buoyancy, because buoyancy depends entirely on denser material sinking and displacing less dense material upward, and in free fall, there's no meaningful up or down for density to sort itself by. So the hot combustion gases don't rise away from the flame the way they do on the ground, and instead, without that convective current constantly hauling fresh oxygen inward from below, the flame has to rely on the far slower process of oxygen simply diffusing inward on its own, drifting in through the surrounding gas by nothing more than random molecular motion, the same gentle process by which a drop of ink slowly spreads through a glass of still water. The result is a flame that burns cooler, dimmer, often nearly spherical rather than teardrop-shaped, sometimes almost invisible to the naked eye,
quietly consuming its fuel in a soft blue globe that behaves less like the flickering campfire flames we know and more like a slow, glowing bubble. Researchers studying these microgravity flames have found that they can behave in unexpected ways, sometimes burning at temperatures too low to produce visible light at all while still consuming fuel, a possibility that has genuine safety implications for spacecraft, since a fire could in principle smolder quietly in a way easy to miss until it had already used up a surprising amount of oxygen or fuel. It's a vivid reminder that so much of what feels like the essential nature of fire, its upward reach, its restless flicker, its teardrop shape, is really the fingerprint of gravity acting on hot gas, not some property belonging to fire alone. Underlying all of this, whether on Earth or in orbit, is the idea of a reaction front, which is simply the boundary where the chemical transformation of burning is actively taking place at any given moment, the thin, moving edge separating fuel that has already burned from fuel that hasn't burned yet. Picture a slow fuse, the kind once used in mining and demolition, a cord impregnated with a slow-burning compound, lit at one end. The flame doesn't leap immediately to the far end. It creeps along, foot by foot, because the heat generated at the burning tip warms the unburned material directly ahead of it, driving that neighboring section up to its own ignition temperature, at which point it too begins to burn, generating its own heat that then warms the next section in turn, and so on, link by link down the cord. This is the reaction front advancing, a self-propagating boundary, carried forward entirely by its own released heat, needing nothing from outside except perhaps a supply of oxygen alongside it. The same idea, at a larger and messier scale, describes how flame spreads across a dry field or through a forest canopy, how it works its way along a curtain, how it travels down the length of a candle's wick as wax at the tip melts, vaporizes, and ignites, each moment's flame lighting the way for the next. It's a strangely patient kind of motion, this creeping advance of a reaction front, and it sets up a natural next question, which is what actually determines how quickly that front can travel, and why some materials let it race along in an instant, while others make it crawl.
That question about speed turns out to depend enormously on which kind of burning you're actually talking about, because the word fire quietly covers several distinct processes that look related but behave in almost opposite ways. Take smoldering, the slow, flameless burning that happens inside a compost heap, inside a poorly stubbed-out cigarette left in a pile of dry leaves, or inside the packed fibers of a mattress. Smoldering has no visible flame at all. There's no reaction happening in a gas cloud above the surface, the way there is with a campfire or a candle. Instead, the burning happens directly at the solid surface itself, in what chemists call a heterogeneous reaction, oxygen molecules diffusing slowly into the material and combining directly with the solid fuel, particularly carbon, left behind after other components have already burned or evaporated away. This is why smoldering can look, to an untrained eye, almost like nothing is happening at all. A cushion might smolder for hours, radiating a faint heat, producing a thin drift of pale smoke, and perhaps the acrid smell of scorching fabric, while looking from across a room like it's simply sitting there. It's one of the more genuinely dangerous forms of burning precisely because it hides so well, because it needs so little oxygen to keep creeping forward, sometimes just the air, trapped between fibers, and because it can persist for a very long time before conditions shift and it flares into open flame. Flaming combustion is the more dramatic cousin, and it depends on something smoldering doesn't need, which is fuel that has been converted into a gas or vapor first. This detail surprises a lot of people the first time they hear it, because a burning log looks like solid wood is what's on fire, but what's actually burning, in the visible dancing flame sense, is a cloud of gases and vaporized compounds released from the wood as heat breaks it down, a process called pyrolysis, and it's that gas cloud, mixing with oxygen from the surrounding air, that produces the flame you see hovering just above and around the log's surface. The solid wood itself is really more like a slow-release fuel tank, cooking off vapor that then ignites a short distance away. This is also, incidentally, why you can sometimes see a gap of clear air between a piece of burning wood and the flame licking above it, a small buffer zone where the freshly released gas hasn't yet mixed thoroughly enough with oxygen to combust. A candle demonstrates this same principle in miniature, almost like a patient little laboratory experiment sitting quietly on a table. The wax itself doesn't burn directly. Heat from the flame melts a small pool of wax near the wick. Capillary action draws that liquid wax up through the braided fibers, and the heat of the flame vaporizes it into a gas, and it's that vapor, not the solid or liquid wax, that actually combines with oxygen in the visible flame. It's a wonderfully self-sustaining little system, almost like a small machine with no moving parts, each stage feeding the next, melting, feeding, wicking, feeding, vaporizing, feeding, burning, feeding, the heat that melts more wax. This is also why a candle flame stays such a remarkably constant size and shape for so long, hour after hour, rather than growing wild the way a bonfire does, since the rate of wax delivery through that narrow wick puts a natural ceiling on how much fuel, vapor, is available at any moment. Wood fires, of the campfire or fireplace variety, are really just this same pyrolysis and vapor combustion process happening at a larger scale and with far less tidy geometry, which is part of why they crackle and pop and throw sparks in a way a candle never does. Trapped moisture and air pockets inside wood, heated rapidly, can expand and rupture with an audible snap. And unlike a candle's clean wax vapor, wood releases a complicated mixture of hundreds of different compounds as it breaks down, which is part of why wood smoke carries such a distinctive, layered smell, part why wood fires burn with those shifting curtains of orange and yellow rather than a single, steady color. Glowing embers are something different again, closer in spirit to smoldering than to flaming. An ember, that chunk of charcoal left after a wood fire has burned down, glows because it's essentially pure carbon combining directly with oxygen at its surface. The same heterogeneous solid phase reaction happening in smoldering, just running hot enough and fast enough to produce that visible orange glow rather than staying invisible. Blow gently on a bed of embers, and you'll often see them brighten, because you're feeding fresh oxygen directly to that surface reaction, temporarily outrunning the rate at which the surrounding air alone would naturally supply it. Gas flames, of the kind seen on a stove burner or in old gas lamps, skip the whole pyrolysis step entirely, since the fuel arrives already in gas form, methane or propane piped or bottled in, ready to combine with oxygen the moment it meets a spark or existing flame. This is part of why a gas flame burns so cleanly and predictably, compared to wood, with a steady, well-defined blue cone rather than a wandering, crackling shape, since there's no complicated solid breaking down unevenly, no moisture hissing off, just a controlled, continuous stream of pre-mixed or near pre-mixed fuel and air. Metal fires occupy a stranger corner of this whole picture, one that runs against a lot of ordinary intuition. Most people don't think of metal as flammable at all, and for the metals in a typical kitchen or workshop, that instinct is basically correct under everyday conditions. But certain metals, particularly some in very fine powdered or shaving form, or certain reactive metals under the right circumstances, can burn with startling intensity, sometimes hot enough to strip oxygen away from compounds that would normally be considered fire suppressants, since some burning metals can continue reacting even in environments that would smother an ordinary wood or gas flame. This is a genuinely specialized category of burning, governed by its own particular chemistry, and firefighters and engineers who work around such materials train specifically for them, precisely because the ordinary intuitions built from watching candles and campfires simply don't transfer. Electrical fires round out this comparison, and they're a useful reminder that the word fire describes an effect more than a single cause. Electricity itself doesn't burn. What happens in what people call an electrical fire is that resistance in a wire or component generates heat, sometimes because of a loose connection, sometimes because a circuit is carrying more current than it was built for, and that heat eventually ignites something nearby. Insulation, dust, a stack of paper, whatever ordinary combustible material happens to be close enough to reach ignition temperature. The electricity is the heat source, not the fuel, which is a distinction that matters enormously for anyone thinking about how such a fire might be approached, since water, so often reached for instinctively around fire, can conduct electricity back through a stream toward whoever's holding it, an old and important piece of caution passed down through generations of firefighters long before anyone fully understood the electrochemistry involved. Laid out side by side like this, smoldering and flaming and glowing, and candle wax and wood and gas and metal and electrical heat all start to look less like variations on one simple thing and more like a small family of related but genuinely distinct processes, each shaped by its own particular fuel, its own particular need for oxygen, its own particular pathway from solid or liquid into the reactive state where burning can actually occur. And that raises a natural next question about all of them, which is what it actually takes, in each case, to stop one once it's begun. Before getting to how a fire is stopped, though, there's something worth sitting with quietly first, something that rises off nearly every fire and yet gets far less attention than the flame itself: the smoke. People tend to think of smoke as a single substance, a kind of gray stuff that pours upward and stings the eyes, but it is really nothing of the sort. Smoke is a mixture, and a shifting one, a cloud made of countless different particles and gases whose exact composition depends on what's burning, how hot it's burning, how much oxygen it's getting, and even how long ago that particular bit of material caught fire. Watch smoke rise from a campfire over the course of an hour, and you are not watching the same thing the whole time. You are watching a slowly changing recipe, one that shifts as the wood dries out, as the flames find more or less air, as green branches give way to charred coals. To understand why smoke varies so much, It helps to go back to that idea of combustion needing enough oxygen to finish its job completely. When a fuel burns with plenty of oxygen and enough heat, the carbon and hydrogen in it can be oxidized all the way to their simplest, most stable end products, carbon dioxide and water vapor, both of which are invisible gases. That's what chemists call complete combustion, and a fire achieving it produces very little visible smoke at all, because almost nothing solid is left floating in the air. But complete combustion is something of an ideal case, rarely achieved perfectly in the messy, turbulent reality of an actual flame. Far more often, some of the fuel's carbon doesn't get fully oxidized. Instead of becoming carbon dioxide, it ends up as something in between, unburned or partially burned fragments of hydrocarbon, tiny particles of carbon that never finished reacting, and it's these leftover fragments, drifting upward on the hot air, that make up the visible portion of smoke. That's incomplete combustion, and nearly every ordinary fire you'll ever see, a campfire, a candle, a fireplace log, is doing a mixture of both at once. Some of the fuel completing its journey to carbon dioxide and water, some of it stalling out partway and escaping as smoke. The particles that give smoke its gray or black color and its familiar smell have a name of their own: soot. Soot is mostly carbon, tiny particles, often smaller than a speck of dust could ever be to the naked eye, and they form when a flame's heat breaks fuel molecules apart faster than oxygen can arrive to combine with all the resulting fragments. Picture a woodworking shop where the person cutting boards is working faster than the person sweeping up the sawdust can keep pace with. The sawdust piles up. Something similar happens chemically inside a flame, especially in the fuel-rich zone near the wick or the log, where hydrocarbon fragments are breaking apart and recombining into larger and larger clusters of carbon atoms before enough oxygen ever reaches them. Some of these clusters grow into tiny solid particles, and if they're small enough and hot enough, they glow, which is actually part of why a candle flame looks yellow rather than blue. Those glowing soot particles, incandescent for a brief instant as they pass through the hottest part of the flame, are what give an ordinary candle or campfire its warm color. Only later, after they've cooled and drifted higher, away from the heat, do those same particles turn from glowing orange specks into the dull gray-black smudge people call soot, the same stuff that blackens a chimney flue or leaves a dark smear on a glass lantern globe. This connects to something that can feel counterintuitive at first. A flame's color is not a simple, reliable guide to its temperature, and a flame's size is not a reliable guide to its danger. People often assume, understandably, that a big roaring orange fire must be hotter and more hazardous than a small quiet blue one, but in many cases the opposite is closer to the truth. That yellow-orange glow, so familiar from candles and campfires and cozy hearths, comes largely from those incandescent soot particles, and while they are indeed hot, a flame that's burning so incompletely that it's throwing off large quantities of visible soot is often not burning as efficiently or as hot overall as a flame that's getting so much oxygen it barely produces any soot at all. A gas stove burner tuned properly burns nearly blue, almost invisible in bright daylight, because it's getting close to enough oxygen to combust completely, leaving very few unburned carbon particles to glow yellow. That blue flame, quieter and less visually dramatic than a campfire, is typically hotter than the campfire is, sometimes by several hundred degrees. Bright, large, and visually impressive is simply not the same axis as hot,
And it is certainly not the same axis as dangerous, since danger from fire has as much to do with what a fire is producing invisibly as with how tall its flames happen to reach. And that brings the conversation to the part of smoke that matters most and shows least, the gases you cannot see at all. Incomplete combustion doesn't just make visible soot particles, it also makes carbon monoxide, a gas with no color, no smell, and no taste, formed when carbon atoms bond with oxygen, but only pick up one oxygen atom instead of the two needed to become the harmless carbon dioxide of complete combustion. Carbon monoxide is dangerous, specifically because it is so unremarkable to the human senses. It doesn't announce itself the way smoke's sting and stench do. It slips into a room quietly, and inside the body it does something almost sly. It binds to the same part of red blood cells that would normally carry oxygen, and it binds there far more readily than oxygen itself does, which means blood-carrying carbon monoxide effectively stops delivering oxygen to the brain and heart, even though the person breathing it may feel, for a while, only tired or mildly headachy, symptoms easy to mistake for something as ordinary as low blood sugar or a stuffy room. This is why enclosed spaces with any incomplete combustion happening in them, a poorly vented fireplace, a charcoal grill brought indoors, a car left running in a closed garage, carry a risk that has nothing to do with visible flame at all, and everything to do with an invisible gas produced quietly alongside it. Firefighters and safety engineers take carbon monoxide extremely seriously for exactly this reason, treating it as a separate hazard from the fire's heat or its visible smoke, something to be measured with dedicated detectors rather than judged by eye or nose, because there is genuinely no other reliable way to notice it in time. Rising above all of this, whether it's mostly soot, mostly water vapor, or some invisible mixture of gases, is the smoke plume itself, and plumes have their own behavior worth understanding, almost like weather in miniature. Hot smoke rises because it's less dense than the cooler air around it, the same principle that lifts a hot air balloon, and as it rises it draws in surrounding air, cooling gradually, spreading gradually, until eventually it loses enough buoyancy to stop climbing and begins to drift sideways instead, forming that familiar mushroom-like layer people notice spreading across a ceiling in a burning building, or flattening out beneath a temperature inversion on a smoky evening outdoors. This is why so much fire safety guidance, drilled into school children for generations, centers on staying low to the ground during a fire. It isn't a matter of tradition or superstition. It reflects the plain physics of buoyancy. The freshest, most breathable air in a smoke-filled room is almost always found near the floor, simply because the hot, particle-laden, oxygen-poor smoke has risen up and away from it, layering the room from the ceiling downward, the way cream might rise and pool at the top of a glass of unshaken milk. A plume's exact behavior, how fast it rises, how far it spreads, how quickly it fills a room from the top down, depends on the size of the fire beneath it, the temperature difference driving it upward, and the shape of whatever space it happens to be rising through. But the underlying logic is consistent enough that people have been able to build reliable safety habits around it for a very long time.
Let's step outside now, away from rooms and ceilings and doorways, and out into open country, because fire behaves differently once it has an entire landscape to work with instead of four walls. Out there, the most important variable, more important in many ways than the fire itself, is something quiet and easy to overlook. How much moisture is sitting inside the plants that make up the landscape's fuel? Foresters and wildland firefighters talk about fuel moisture the way a baker talks about the water content of dough, because it changes everything about how the material responds to heat. A green leaf in springtime might be 60 or 70% water by weight, and before any of that leaf can actually burn, all of that water has to be driven off as steam first, absorbing a tremendous amount of heat in the process, the same latent heat of vaporization that makes a pot of water so stubborn to boil dry. That's why live, healthy vegetation resists burning even when flame touches it directly, sizzling and steaming rather than igniting. In much the same way, a wet log refuses to catch in a campfire no matter how long you hold a match to it. Dead fuel is a different story entirely. A fallen branch, a curl of dry grass, a mat of last autumn's leaves, these lose their moisture to the surrounding air continuously, drying and dampening in a slow rhythm that tracks the humidity, the sunlight, and the season, sometimes described by researchers in terms of a time lag, a rough measure of how quickly a given piece of fuel equilibrates with the air around it. A thin blade of grass might respond to an hour of dry wind, drying out almost as fast as the air around it changes, which is why grass fires can ignite and spread within hours of a dry spell. A fallen log, thick and dense, might take weeks to fully dry out, and just as long to fully re-wet, which is part of why a forest can stay dangerously flammable long after the last obviously dry, sunny day, the moisture locked deep in the heavier fuels, lagging quietly behind the weather. Wind is the second great variable, and it does far more than simply push flames sideways, though it certainly does that too. Wind tilts a flame forward, angling it toward fuel that hasn't caught yet, preheating that fuel through direct contact and radiant heat, well before the flame front actually arrives, the way a hairdryer aimed just ahead of your hand warms your skin before it ever touches it. This preheating effect can dramatically accelerate a fire's spread compared to the same fire burning on a still day, and it also explains a pattern that puzzled early fire researchers. Wind-driven fires tend to spread in a narrowing, elongated shape, sometimes compared to the outline of a teardrop or an arrowhead, racing forward along the wind's direction while spreading only slowly out to the sides and barely creeping backward at all against the wind. Firefighters use this predictable shape constantly, sketching it out on maps to anticipate where a fire is likely to be hours from now, because a fire's edges don't advance uniformly in every direction the way ripples do on a pond. They stretch unevenly according to whatever the air above them happens to be doing. Terrain complicates this picture in a way that surprises a lot of people the first time they hear it explained, because fire has a strong preference for burning uphill, and the reason has nothing to do with wind at all. It comes back, once again, to that same rising plume of hot gas. On a slope, flames and hot air rising off burning fuel don't just drift straight upward into open sky the way they would on flat ground. The hillside itself, tilted beneath them, sits closer to that rising heat than it would if the ground were level, so the vegetation just uphill of the fire gets preheated and dried out far more intensely and far sooner than vegetation on flat terrain ever would. It's a little like holding your hand at a fixed distance above a candle flame versus tilting your hand so it leans in closer to the same flame at an angle. The tilted hand feels far more heat for the same distance because it's intercepting more of what's rising. This is why a fire, creeping gently across flat ground, can suddenly race up a hillside once it reaches the base of a slope, and why firefighters are trained with an almost instinctive wariness about ever positioning themselves directly above a fire on sloped ground, since that is very often exactly where the fire is heading next, and heading there quickly. When wind, slope, and dry fuel all align at once, Wildland fire can shift into behavior that goes well beyond simple spreading, and one of the most dramatic examples is spotting, where the fire essentially throws pieces of itself ahead of the main front. Strong convective currents rising off an intense fire can loft burning embers, sometimes called firebrands, hundreds of feet into the air, and the wind can then carry these glowing fragments a mile or more downwind before they finally settle back to earth. If they land somewhere dry enough, they can ignite an entirely new fire long before the original flame front ever physically arrives there, which is part of why wildland fires can seem to leap forward unpredictably, appearing suddenly on the far side of a river or a highway that should, by any simple accounting, have served as a barrier. This same ember-throwing behavior is also one of the primary ways wildfires ignite homes at the edge of wildland areas, not always through a wall of direct flame arriving at the property line, but through a single wind-carried ember finding its way into a gutter full of dry leaves or a gap beneath a wooden deck, smoldering there quietly for a while before anyone notices. Crown fire represents another distinct level of wildland fire behavior, and it helps to understand what it actually is, rather than treating it as simply a fire that happens to be tall. Most wildland fire, most of the time, is a surface fire, creeping and spreading through grass, fallen leaves, and low brush close to the ground. Under the right combination of dry fuel, wind, and what firefighters call ladder fuels, meaning shrubs and low branches that physically bridge the gap between the ground and the treetops, a surface fire can climb upward and establish itself in the canopy, becoming a crown fire that spreads through the treetops themselves, sometimes even racing ahead of the surface fire beneath it, torching one treetop and then another as radiant heat and wind-blown embers ignite dry needles or leaves at canopy height. Crown fires are generally far more intense and far more dangerous than surface fires, in part because they burn so much more fuel at once, and in part because that latter fuel connection means the fire is drawing on both the ground layer and the canopy layer simultaneously, feeding two fuel beds instead of one. It's worth pausing here on something easy to lose sight of once all this talk turns to danger and intensity and homes at risk, which is that fire, in wildland settings, is not fundamentally an intruder or an aberration. Long before there were subdivisions built at the edge of forests, or towns nestled into fire-adapted grasslands, many ecosystems around the world evolved alongside regular, recurring fire, shaped by it in ways that are sometimes easy to overlook. Certain pine species carry cones, sealed shut with a waxy resin that only melts and releases their seeds after exposure to real fire heat, a trait called serotiny, meaning the tree essentially times its own reproduction to burning. Some grassland and savanna ecosystems depend on periodic fire to clear out woody encroachment and recycle nutrients back into the soil, nutrients that would otherwise stay locked up in slowly decaying plant matter for years. Indigenous peoples across many parts of the world understood this rhythm intimately and long practiced deliberate, controlled burning as a land management tool, setting smaller, cooler fires under favorable conditions to reduce fuel buildup and encourage the growth of particular plants long before the term prescribed burning existed in any official capacity. Let's move now from fire as something that happens to fire as something that gets measured, because at some point in the history of human curiosity, people stopped simply watching flames and started asking, quietly, precisely, how much? How much heat is actually released when this piece of wood burns, or this lump of coal, or this spoonful of sugar? That question turns out to be surprisingly hard to answer just by looking, because heat doesn't sit still long enough to be weighed the way a solid object can be weighed. So scientists built devices to trap it, and the simplest and oldest of these is called a calorimeter, from the Latin calor, meaning heat. The basic idea is almost embarrassingly simple. You burn something inside a sealed container, and you surround that container with a known quantity of water, and then you just watch the water's temperature climb. Water has a very consistent, well-understood relationship between how much heat it absorbs and how much its temperature rises. So if you know exactly how much the water warmed and exactly how much water there was, you can work backward to calculate exactly how much heat the burning released. It's a bit like trying to figure out how hard someone pushed a swing by measuring how high it went afterward, rather than trying to measure the push itself while it's happening. This is, incidentally, where the modern nutritional calorie comes from, and it's one of those facts that quietly rearranges how you think about food. A calorie, in the original scientific sense, is simply the amount of heat needed to raise 1 gram of water by 1 degree Celsius. When nutritionists in the 19th century wanted to know how much energy a food could provide to the human body, they turned to something called a bomb calorimeter, a small, heavily reinforced steel chamber that could hold a sample of food, packed with pure oxygen, then ignited electrically and allowed to burn completely inside that sealed container, submerged in water. The food is, in a very literal sense, set on fire and burned to ash, and the resulting temperature rise in the surrounding water tells you its caloric content. It's a strange thought to sit with as you drift toward sleep, that the number on a nutrition label traces back to someone, somewhere, actually incinerating a sample of that exact food, in miniature, inside a steel bomb. Calorimetry answers the question of how much energy a fire releases, but it doesn't tell you much about what is actually happening at the molecular level while the flame burns, and for that, scientists developed an entirely different tool, one that relies not on trapping heat, but on reading light. This is spectroscopy, and it works because every element and every molecule, when it gets hot enough to glow, doesn't just emit generic light. It emits very specific wavelengths, specific colors, determined by the exact structure of its atoms and how their electrons are arranged. If you pass the light from a flame through a prism, or a more refined instrument called a spectroscope, instead of seeing a smooth, continuous rainbow, you see a pattern of distinct bright lines at particular positions, almost like a barcode, and that barcode is unique to whatever elements are present in the flame. This is genuinely how chemists in the 19th century discovered several new elements, including cesium and rubidium, both named for the colors of the spectral lines that gave them away, cesium for a sky blue line and rubidium for a deep red one. It's a lovely idea, really, that a flame is not just heat and light in some vague sense, but a kind of signature, a message written in color that tells you, if you know how to read it, exactly what's burning. Once you can measure how much heat a fire releases and understand something of its chemical signature, the next natural question becomes how a fire moves, and this brings in the idea of a flame front. Picture a sheet of paper lying flat, with a match touched to one corner. The flame doesn't leap instantly across the whole sheet. It advances as a visible edge, a boundary between burned and unburned material, creeping forward as heat from the burning zone
warms the neighboring unburned fuel to its ignition point. That boundary is the flame front, and its speed, called the flame speed, depends on a tangle of factors, including how flammable the fuel is, how much oxygen is available, and how the surrounding gases are moving. In a calm room, a flame front might crawl along steadily and predictably. But introduce turbulence, wind, or pressure changes, and that same flame front can accelerate dramatically, sometimes to the point where it transitions into something else entirely, a detonation, where the flame front is moving faster than the speed of sound in that particular gas mixture. This is one of the more genuinely unsettling ideas in combustion science, that under the right unfortunate conditions, an ordinary flame can transform into a supersonic shock wave, and it's a large part of why fuel storage and industrial gas handling are treated with such elaborate caution. Understanding flame fronts and how they can be encouraged, shaped, or contained turns out to be central to a huge amount of engineering, because so much of the machinery that moves the modern world is, at its core, a carefully managed fire. Take the internal combustion engine, the kind that for over a century sat under the hood of most cars. Inside each cylinder, a small, precisely timed explosion of fuel and air pushes a piston, and the engine's entire performance depends on controlling exactly when and how fast that flame front spreads outward from the spark plug. If the timing is off, if the flame front moves too early or too erratically, you get what mechanics call knocking, a rough, uneven combustion that wastes energy and can damage the engine over time.
Gas turbines, the kind used in jet engines and in power plants, work on a related but distinct principle, maintaining a continuous, stable flame inside a combustion chamber, rather than a series of discrete explosions, with fuel and compressed air mixing and burning steadily as they're forced through the engine, and the resulting hot expanding gases spinning turbine blades to generate thrust or electricity. And industrial furnaces, whether smelting metal ore or firing ceramics or generating steam for a power plant, are essentially fire-tamed into a box, engineered so that combustion happens as completely and efficiently as possible, with every wisp of unburned fuel representing wasted energy and unnecessary pollution. Rockets push this idea to an extreme that's almost dizzying to think about. A rocket engine is, in the simplest terms, a controlled explosion aimed in one direction, but managing that controlled explosion requires solving problems most other combustion engineering never has to face, because a rocket typically has to carry its own oxidizer along with its fuel, since there's no atmosphere to draw oxygen from once it leaves the ground. Some rockets burn liquid fuel and liquid oxidizer pumped together into a combustion chamber at rates that would be almost impossible to picture. Tons of propellant burning every second, releasing energy so violently and so fast that the resulting exhaust gases shoot out the nozzle at several times the speed of sound. Other rockets use solid fuel, essentially a carefully shaped, densely packed block that burns from the inside out along a precisely engineered surface, its burn rate controlled almost entirely by the geometry of that internal shape rather than by any valve or throttle. If understanding combustion well enough to build engines and rockets represents fire pushed to its productive extreme, then understanding combustion well enough to extinguish it represents the opposite, equally careful skill, and it rests on the same basic chemistry in reverse. Fire needs fuel, oxygen, and heat, sustained together in a particular arrangement, and every method of extinguishing a fire works by removing one of those three. Water cools the fuel below its ignition temperature
carrying heat away as it evaporates. A fire blanket or foam smothers the flame by cutting off its oxygen supply. Some chemical extinguishers work by interrupting the actual chemical chain reaction of combustion at the molecular level, scavenging the reactive intermediate particles that keep the flame self-sustaining, which is a subtler and in some ways more elegant trick than simply cooling or smothering. For all this precision, though, it's worth remembering that laboratory models of combustion, however carefully measured and mathematically described, are always simplifications, tidy approximations of something that in the real world tends to be messier, more turbulent, and more stubbornly resistant to clean equations than any textbook diagram quite lets on.
That stubborn messiness becomes almost comic once you leave the surface of the earth and start asking whether fire, in any form we've been describing, exists anywhere else at all. Because much of what glows and burns and radiates out in the wider universe isn't fire in the sense we've spent all this time carefully building up, chemical oxidation, fuel and oxidizer racing toward each other, heat and light released as bonds break and reform. Some of the most spectacular light shows in the cosmos work through entirely different physics, and untangling that distinction turns out to be one more quiet, satisfying correction to the intuitive picture most of us carry around without examining it. Start with the most obvious candidate, the one that seems, on first glance, like the biggest fire imaginable, the sun. It's hot, it's bright, it burns your skin if you stand under it too long without protection, and for most of human history, it was reasonable enough to imagine it as some kind of enormous celestial bonfire, a ball of flame suspended in the sky. Ancient observers who thought this way weren't being foolish. Fire was the most powerful source of heat and light they knew, so it made sense to reach for that comparison when trying to explain the most powerful source of heat and light visible to them. But the comparison breaks down almost immediately once you do the arithmetic. Ordinary combustion, even on the grandest scale, requires fuel and oxygen, and it releases energy at a rate limited by how fast those two things can find each other and react. If the sun were somehow a giant sphere of burning coal or hydrogen gas combusting with oxygen the ordinary way, calculations going back to the 19th century show it would have exhausted its fuel and gone dark in a matter of thousands of years, not the billions of years geologists were already finding evidence for in the rocks beneath their feet. Something else had to be going on, and it took until the 20th century, with a deeper understanding of atomic nuclei, for anyone to work out what. The sun shines because of nuclear fusion, not chemical combustion, and the difference between those two processes runs all the way down to what's actually happening at the smallest scale. Combustion rearranges the outer electrons of atoms, breaking and forming chemical bonds, releasing the comparatively modest energy stored in those bonds. Fusion, by contrast, reaches into the nucleus itself, the tiny dense core of the atom, and forces hydrogen nuclei to slam together with enough violence to fuse into helium, releasing an amount of energy so much larger than any chemical reaction that the two processes are barely worth comparing on the same scale. This can only happen under conditions that don't exist anywhere on the Earth's surface. Temperatures near 15 million degrees at the sun's core, and pressures created by the crushing weight of the sun's own enormous mass pressing down on itself from every direction. There's no flame front there, no visible edge between burned and unburned material spreading outward the way a candle flame spreads through wax vapor. It's a continuous, self-sustaining nuclear reaction, held in balance by gravity squeezing inward and the energy of fusion pushing outward,
a balance so stable it's kept the sun shining at roughly the same output for billions of years. What we see as sunlight isn't flame at all. It's the glow of something unimaginably hot, radiating light the way any hot object does. The same physics, just turned up to a scale that has no everyday equivalent. Meteors offer a different kind of correction to intuition, closer to home and easier to picture, since most people have actually seen one streak across a night sky. It's natural to describe that streak as the meteor burning up, and in casual conversation, there's nothing wrong with saying it that way. But the light of a meteor mostly isn't combustion either. A meteor, really just a small chunk of rock or metal debris left over from the early solar system or shed by a passing comet, enters the atmosphere at extraordinary speed, often tens of kilometers per second, far faster than a rifle bullet. At that speed, it's slamming into air molecules so rapidly and so continuously that it compresses the air directly in front of it, and compressing a gas that quickly heats it dramatically, the same principle, scaled up enormously, that makes a bicycle pump warm at the nozzle when you push the handle down fast. The compressed air ahead of the meteor becomes a sheath of superheated, glowing plasma, and it's largely that glowing air, not the meteor itself, producing the streak of light you see. Meanwhile, the meteor's own surface is being stripped away, layer by layer, in a process called ablation. Tiny fragments and vaporized material shearing off from the friction and heat, most of it burning away completely before ever reaching the ground, which is why the vast majority of meteors never survive to become meteorites resting in someone's hand. There is genuine chemical reaction happening in some of that ablated material as it vaporizes and interacts with atmospheric oxygen, so it isn't entirely wrong to invoke burning. But the dominant, breathtaking brightness of a meteor streak comes from compressed, superheated gas glowing with the meteor's own kinetic energy converted into heat and light, a process closer to what happens to a spacecraft during atmospheric re-entry than to anything happening in a fireplace. Spacecraft re-entry, in fact, makes this same point from the other direction, deliberately engineered rather than accidental. When a capsule returns from orbit, it's traveling at many times the speed of sound relative to the thickening air below it, and the heat generated as it plows through the atmosphere isn't primarily friction in the simple sense most people imagine, rubbing surfaces creating warmth. It's the same compression heating that lights up a meteor, air molecules crushed and superheated ahead of the vehicle into a glowing plasma sheath that can reach temperatures of several thousand degrees, hot enough to require heat shields specifically designed to absorb or ablate that energy away, rather than let it reach anything or anyone inside. Astronauts inside a returning capsule watch flame-colored plasma streak past their windows, and it looks for all the world like they're wrapped in fire, but what's glowing outside the glass is compressed, ionized air, not combustion in the oxidation sense at all. Fire behaves strangely in spacecraft in a second, quieter way too, one that has nothing to do with re-entry heat and everything to do with gravity, or rather its absence. Ordinary flames on Earth owe much of their familiar teardrop shape to convection, hot combustion gases rising because they're less dense than the cooler air around them, dragging fresh oxygen in behind them as they go. In the near weightlessness of an orbiting spacecraft, that upward pull essentially disappears, and flames respond by curling into faint, spherical, blue-tinged globes instead, burning more slowly, more quietly, and relying on the sluggish diffusion of oxygen rather than any brisk convective current to keep themselves fed. Researchers have deliberately studied these strange, slow-burning orbs aboard orbiting laboratories, partly out of scientific curiosity about how combustion works, when one of its usual driving forces is removed, and partly for a far more practical reason, since understanding how fire behaves, spreads, and can be extinguished in microgravity is essential to keeping astronauts safe in a sealed environment where there's nowhere to run from smoke.
Even something as seemingly earthbound as volcanic glow turns out to carry a similar lesson about not trusting appearances too quickly. Molten lava pouring from a fissure or lighting up a caldera at night looks, to any reasonable eye, like fire on a colossal scale, and the word fire shows up constantly in descriptions of eruptions going back centuries. But that orange and red glow is simply incandescence, the light given off by rock heated to temperatures well over 1,000 degrees, the same physics that makes a blacksmith's iron glow in the forge before it's ever struck. There's no combustion reaction driving the light itself, no fuel oxidizing to release that particular glow, just extraordinarily hot matter radiating energy the way hot matter always does, whether it's a star, a stove burner, or a river of molten stone. That distinction between glowing and burning is worth sitting with for a moment, because it quietly explains something that trips up even people who've thought about fire for years. The difference between a flame that behaves in a smooth, orderly way and one that seems to writhe and tear itself apart. Watch a candle in a perfectly still room, and the flame holds a shape you could almost trace with a pencil. A calm blue base narrowing into that familiar yellow teardrop, barely moving except for a faint, slow flicker. Watch a bonfire, or the flame from a cracked gas line, or the roaring output of a jet engine's afterburner, and you're looking at something else entirely, a chaotic tumble of hot gas folding over itself in ways that seem to defy any simple description. Both are combustion. Both involve fuel meeting oxygen and releasing heat and light. But one is what scientists call laminar, and the other is turbulent, and the line between them turns out to be one of the more genuinely difficult problems in all of physics, not just in the specific study of fire. Laminar flow, whether in a flame or in water moving through a pipe, means the fluid moves in smooth, parallel layers, each one gliding past its neighbor without much mixing between them. A thin candle flame is laminar because it's small and slow enough that the rising column of hot gas stays orderly, sheet sliding past sheet, the way cream can be poured gently into coffee and, for a moment, hold its shape as a distinct swirl before it inevitably breaks apart. Turbulence is what happens when that gentle order collapses, when the flow becomes fast enough or the temperature differences sharp enough that tiny disturbances stop damping themselves out and instead grow, cascading into eddies, and those eddies spawn smaller eddies, and so on, down through scales too small to see, until the whole thing is a churning, three-dimensional tangle. The transition from one state to the other isn't a hard line so much as a threshold that depends on the balance between the forces trying to keep the flow orderly and the forces trying to disrupt it. A ratio physicists capture in something called the Reynolds number, which compares inertia, the fluid's tendency to keep moving the way it's already moving, against viscosity, its internal stickiness, its resistance to being deformed. Cross a critical value of that ratio, and smooth flow tips over into chaos, sometimes gradually, sometimes with startling suddenness, the way a candle flame in a draft-free room will hold its shape right up until a small gust arrives and it erupts into flickering disorder. This matters for understanding fire because turbulence changes almost everything about how a flame behaves. A laminar flame burns at a fairly predictable rate, limited mostly by how quickly heat and fuel vapor can diffuse across that thin reaction zone we talked about earlier in this account. The same slow molecular handshake happening again and again in an orderly line. A turbulent flame, by contrast, gets a kind of assist from the chaos itself. All that folding and tumbling dramatically increases the surface area where fuel and oxygen actually meet, wrinkling the flame front into a far more convoluted shape than any smooth cone or teardrop, and that increased contact area lets the fire consume fuel much faster than diffusion alone would allow. It's part of why a turbulent flame in a furnace or an engine can release energy so much more rapidly than a candle ever could, and it's part of why engineers spend enormous effort trying to either encourage or suppress turbulence, depending on what they're building, wanting it inside a combustion chamber where fast, complete burning matters, but dreading it in a wildfire, where turbulence can make flames leap unpredictably and spread far faster than any simple model would suggest. And this, honestly, is where fire stops being simple, even for the people who study it professionally. A candle flame looks like the most modest object imaginable, something a child could draw with 3 or 4 strokes of a crayon, and yet fully modeling what's happening inside it, predicting its exact shape, its flicker frequency, the precise path of every eddy of hot gas rising off its surface, remains a genuinely hard computational problem. The equations that govern fluid motion, named after the mathematicians Claude Louis Navier and George Gabriel Stokes, who developed them independently in the 1800s, are famous for being almost impossible to solve exactly, except in the simplest of situations. Add combustion chemistry on top of that fluid motion, dozens or even hundreds of interacting chemical reactions happening simultaneously at different rates, depending on local temperature and concentration, and you get a problem so tangled that even today's most powerful supercomputers can only approximate it, breaking the flame down into a grid of tiny cells and calculating, moment by moment, how heat and mass and momentum move between them. It's a small, almost humbling irony that something humans have used with total confidence for hundreds of thousands of years, something a person can create with 2 sticks and enough patience, still sits at the edge of what our best mathematics and our fastest machines can fully capture. There's one more layer to fire's strangeness, worth mentioning before this account winds down, and it involves a word people sometimes reach for without quite meaning it: plasma. Ordinary flames, even hot ones, are not plasma in the strict sense that physicists use the term, which refers to a state of matter where a significant fraction of atoms have been stripped of their electrons entirely, leaving behind a soup of free-floating ions and electrons that behaves less like a gas and more like an electrically charged fluid, responsive to magnetic fields in ways ordinary matter simply isn't. The interior of the sun is plasma. The glowing gas inside a fluorescent tube or a neon sign is plasma. A candle flame, even a bonfire, isn't nearly hot enough to ionize its gases in any substantial way, though a flame does contain a very small population of charged particles, enough that a flame can be gently pushed or bent by a strong static electric field, a fact demonstrators sometimes use to startle an audience by making a candle flame lean toward a charged rod as if it were alive and curious. Where, 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 where,
where, where, where, where, where, where, where, where, where, where, where. But truly extreme flames, the kind found in certain welding arcs, in lightning, in the exhaust of a rocket engine, or in a nuclear fireball, do reach temperatures high enough to genuinely ionize the surrounding gas, crossing over from ordinary combustion into something closer to that fourth state of matter, hot enough that electrons are torn loose from their atoms entirely, rather than merely rearranged among them, which is part of why such extreme flames glow with colors and behave with an intensity that ordinary fire, never quite achieves. All of this energy, whether it's dispersing gently from a candle or violently from a plasma arc, ultimately obeys the same quiet accounting principle threaded through everything discussed so far. Every joule released by breaking and reforming chemical bonds has to go somewhere, and it goes, in the end, into three familiar places, into light radiating outward in all directions, most of it in visible infrared warmth, rather than the visible glow our eyes happen to catch, into heating the surrounding air and any nearby surfaces through direct contact and convection, and into the faint, restless jostling of molecules that we simply call temperature, the same trembling motion that was there at the very beginning of this account, when a single spark first found a hospitable arrangement of fuel and oxygen and began the chain reaction that would eventually engulf an entire log, or light an entire room, or curl into a small blue orb aboard a spacecraft 250 miles above the Earth. And so, however far this account has wandered, into rocket exhaust and volcanic glow, and the electron shells of ionized gas, it always comes back to that same small, patient molecular process, bonds breaking, energy releasing, new bonds reforming into water vapor and carbon dioxide, over and over, trillions of times a second, in a flame no larger than your thumb, or as vast as a forest fire visible from orbit.
It's a simple story, told at an almost unimaginable scale of repetition, quiet chemistry running underneath something that looks, to the naked eye, like nothing so much as light and motion and warmth. Rest well.